Hello, business calc students. We are not only on homework number 3, but we've made our way to the golf course. I hope you are enjoying your day, and let's get right into homework number 3. Okie dokie, starting with question number 2 in our supplementary problems here. Find the equation of the tangent line to f of x equals x to the 5th minus 4x squared plus 3 at the point -1 comma f of -1. Okay, so that's the information we're given. So if you're coming into this, you are probably told in class that, or at the very least, how to take the derivative, and by extension, that you need to take the derivative of this function in order to solve the problem. So problem is in business calculus that they don't really take you through the step-by-step formulation of why you take the derivative. Um, at least there's just a little bit of gap left that is helpful to bridge here. So I hope you'll indulge me here, and I hope it's beneficial to you and your understanding of how this stuff works, why it works. And it harkens back to, it refers back to some of what we talked about in the previous homework, which is about the instantaneous rate of change and approximating the instantaneous rate of change. Where previously we had, I remember there was we had some kind of f of 2 minus f of 0 over 2 minus 0. And we were estimating, or maybe it was p, but we were estimating what was happening at x equals 1. And I mentioned that if you were to take that distance smaller and smaller, so let's say f of 1.1 minus f of 0.9 over 1.1 minus 0.9. So you can tell the bottom is getting smaller and smaller. It's getting closer and closer to 0, which is what we want. We can't have it actually get to be equal to 0 on the bottom because we can't divide by 0 because that would be undefined. So, but taken to the extreme, what this means is, so let's take basically, again, what's happening here is the change between, let's call this A and let's call this B. So B minus A, the change between B minus A, or the difference between B minus A, B and A and B, is getting closer and closer to 0. So we're going to define this delta X as B minus A. Okay. And again, I just want you to follow along here. This is just for your understanding. We'll go back to just going through the problems in a little bit here. But this is key to really understanding how the derivative works, why it works, etc. So there's this concept of limits, which you guys don't cover in business calc, which they do go over in the regular calc, that is helpful in understanding this. So again, we're taking this denominator of this thing, this B minus A, our delta X, and it's getting closer and closer to 0. So we're not saying that it ever equals 0, but it's getting so close to 0 that it may as well be without being exactly 0. And we're going to take that limit of this problem, of this fraction here, and we're going to generalize. We're going to call it, well, we're going to take our starting point, because again, what we're trying to estimate is the instantaneous rate of change at some particular x value. So let's call this f of x plus delta x minus f of x over x plus delta x minus x. Okay. And this is akin to where a is equal to x and therefore b is equal to x plus delta x, right? So then when we have b minus a, that's equal to x plus delta x minus x. All of this is the same, right? It simplifies down to the same thing. So this b minus a, the denominator here, we can see the denominator simplifies to just delta x. So sometimes you may also see, if you were to look on the online or in some kind of textbook, you could also see this as limit as h approaches 0, and that h again is the same thing as this delta x. So f of x plus h, just to differentiate it as a different variable. Sometimes you'll see it as that. I like explaining it with the delta x at first, just so that you understand that it's the same thing as this change along the x-axis of effectively, again, yeah, this so it's like you're taking two different points and you're connecting a line in between, and you're solving for the slope of the line. That's what we're trying to do here, right? So if you remember back to the previous situation, what we're doing here is we are estimating the slope of this of any given line. So we're taking two different points. It's again this delta y over delta x, right? And there's that delta x again. So it's as the delta x is getting really close to 0. And the delta y is just whatever it is. So again, the concept of what we're doing is we're bringing these two, if this is x and this is x plus delta x, we're bringing delta x close to 0, which means this point here is getting really, really close to this point. And so as they get closer and closer together, they almost, if not truly, form into one single point. But the proposition is that as this delta x approaches 0, the fraction that we get approaches the instantaneous slope of the curve. And again, that can be also represented as the slope of the tangent line to the curve, if that makes sense. So again, the tangent line is a line that simply touches the graph, touches the curve at a single point. And the slope of that tangent line is equivalent to the instantaneous slope of the curve at that particular point. So we're going to, for this problem and all tangent line problems, we're going to first solve for the slope of the tangent line, or in other words, the slope of the curve at that point. And then we're going to use the intersection of the point of the tangent line and the graph, right? So that's at this -1 comma f of -1. That's our x comma y. And then we're going to get the slope from this after taking the derivative, which is that effectively that process we went through, but we're going to have a rule that summarizes what taking the derivative looks like. And we'll explain a little bit more of that in a second. But we have this m, we have x, and we have y that we're going to plug into y equals mx plus b, and we're going to solve for b. And then we're going to represent it as y equals mx plus b, but then we're going to plug in whatever the values we get for m and b, representing it like that. So that's the process that we're going to go through here. And now we can actually just do that process. So in taking the derivative, I'm going to just briefly take us through a simpler function to see how this works. Let's just call it x squared, okay? So again, that limit as delta x approaches 0 of f of x plus delta x minus f of x over it's x plus delta x minus x, so it's just delta x on the bottom. So in this situation, that's going to be x plus delta x. So wherever you see x in the original equation, you plug in x plus delta x. That's what this means, f of x plus delta x. So x plus delta x squared minus x squared all over delta x. And this is still limit as delta x approaches 0. So we're going to expand this first term, this first thing. It's going to be x squared plus 2x delta x plus delta x squared minus x squared all over x, delta x rather. And that's still, sometimes even I forget this stuff, limit as delta x approaches 0. So this x squared minus x squared cancel. Each of the top two terms have a delta x. So that's going to be equal to the limit as delta x approaches 0 of delta x times 2x plus delta x all over delta x. So that's where we can get these to cancel out. And now we can plug in delta x equals 0, right? So everything we did up to this point was ultimately for the purpose of getting rid of this delta x in the denominator, because if we were to just straight plug in this delta x equals 0, then we have a problem. We would have the undefined problem. But now that we just have this delta x in the numerator, it's like 2x plus 0 basically, or something really close to 0. It may as well just be this 2x. So that's what we get when we plug in delta x equals 0, because there's no rules against it ultimately in this situation. So we get the derivative, right? So the derivative of x squared ends up being 2x. Okay? So that generalizes into what we get as the power rule. If we were to do other examples, we would find this pattern where for some f of x equal x to the power of n, f prime of x, that's a notation for the derivative. There's a couple other ones, but this one for now works. F prime of x is equal to n times x to the n minus 1. And I'm sure you've seen that now in class. But like we had x squared, the derivative of that becomes 2, right? So you bring down the exponent. So 2, and then you have x to the 2 minus 1. So that's 2x to the 1, which is equal to just 2x. So that's the pattern we're going to follow. Okay. All this is about recognizing patterns. That's what these formulas and equations, that's what they're all about. So we're going to revisit that power rule if we need to, but hopefully it will make sense. So m is going to be equal to f prime of negative 1. But before we do f prime of negative 1, we want to find f prime of x, and we're going to apply that power rule. So we're going to bring down the exponent and then subtract the exponent by 1. So it's going to be 5x to the 4th, right? So bringing that 5 down and then subtracting 1 from 5 to get 5x to the 4th, minus 4 times 2, 8 times x to the 2 minus 1, which is 1. So now the power rule technically applies, so that x to the n, f prime of x equals n times x to the n minus 1. It applies for all n not equal to 0, right? So the original n cannot be equal to 0. Why? Because if n is equal to 0, so if we have x to the 0, that actually equals 1. So this again is f of x equals, which is really a y equals. So if y were equal to 1, for example, so let's say we have our axes here. This is the x-axis, the y-axis. This is the line y equals 1. And if you know what type of equation this is of the form y equals c, a constant. Well, what's the nature of a constant? A constant is something that is not changing. And the derivative, another way of phrasing the derivative, is the rate of change. So what is the rate of change of something that isn't changing? F prime of x is equal to 0, right? The derivative of any constant is equal to 0. And another way you can look at that is, again, the slope of this line, right? So this is a line, y equals 1 is a line of the form y equals 0x plus, in general, some constant, but in this case, plus 1, right? So the 0 times x is equal to 0, plus 1 is equal to 1. So the slope of this line, right, y equals mx plus b, m is equal to 0. So just so you understand that fully, anytime you have a constant, a straight horizontal line, right? So whether it's y equals 1 or y equals 10 or y equals negative 38, all of those, the derivative of all of those horizontal lines, all of those constants is going to be 0, 0, 0, 0, 0, 0. Okay, so back to the problem. I like to hammer that home because sometimes people don't know that or don't remember that. They're like, oh, the derivative is 3. And it's like, no, it's a constant. The rate of change of a constant is 0. Okay, so the derivative of f of x, f prime of x now, is 5x to the fourth minus 8x, period. F prime of negative 1, now we can plug in negative 1 in for x. So 5 times negative 1 to the power of 4 minus 8 times negative 1 to the power of 1, which is just itself. Negative 1 to the fourth. So negative 1 times negative 1 times negative 1 times negative 1. Do that in your head if you want to. Figure it out. Negative 1 to the fourth is positive 1. So whenever you have negative 1 to some power, if it's an even power, it's going to be positive 1. If it's an odd power, it's going to be negative 1. And that goes for any negative number that you're raising to a power. If the power is even, it's going to be positive, whatever it is. If it's odd, it's going to be negative, whatever the result is. So negative 2 to the third, for example, would be negative 8, but negative 2 to the negative 2 to the fourth would be positive 16. It's going to be 5 minus 8 times negative 1. So 8 times negative 1 is negative 8. So negative times that, so it's positive 8. So f prime of negative 1 is equal to 13. So again, that's equal to m. But we don't know what f of negative 1 is, so let's do that. F of negative 1 equals negative 1 to the fifth minus 4 times negative 1 squared plus 3. So negative 1 to the fifth is going to be, again, negative. So negative 1 minus 4 times positive 1, so minus 4 plus 3. So negative 5 plus 3 is negative 2. So now our equation of the tangent line, we have our x is negative 1, our y is negative 2, our m is 13, and we need to solve for b. So negative 2 is equal to 13 times negative 1 plus b. Negative 2 equals negative 13 plus b. B is equal to 11, positive 11. We move that 13 to the other side. 13 minus 2 effectively. Okay, so our equation of the tangent line is y equals 13x plus 11. Crazy, right? We got there. Question 3. So in this is similar to the table that we had in homework number 2, but now we are including some derivatives. And we also get introduced to the idea of composite functions and also some of the, quote, derivative rules at play here. So we'll break those down step by step. So the table below gives some values for functions f of x, g of x, and their derivatives f prime of x and g prime of x. Use this table to evaluate the following expressions. So A, we have 6g prime of 4. So the first step here is to recognize that this is equal to 6 times g prime of 4. So that's one of the derivative rules. It's the constant multiple rule. So if you have 6 times the derivative, it equals, or rather, if you have 6g, which is like 6 times the function itself, 6 times g, and then you take the derivative of that, that equals 6 times just the derivative portion. That makes sense. So you should have some kind of sheet with all the different derivative laws, but I'm just explaining that kind of in more simple terms of how that applies. So you're instead of looking at 6 times the function and then taking the derivative of that result, right? So 6 times the function would be the amplitude or the height, the y value of the original function g of x gets multiplied by 6, and then you take the derivative of that result. That equals just doing 6 times the result or the reading of the g prime value. Okay, so in this case, what that means is it's 6 times. So we look at g prime of 4. So we go 6 times -5, which is -30. Boom. B. Now we have f plus 3g prime of 4. So that's equal to, now we have not only the constant multiple law, but we have this sum law. So this is equal to f prime of 4 plus 3 times g prime of 4. So I did this part out just like we did part A, where we have 3 times g prime of 4 instead of 3g in parentheses prime of 4. So you could have split that up into 2 different steps where you're splitting it up at the level of the sum and then also doing the constant multiple in a separate step. But I did it all in one step here. So in other words, if you add 2 functions together, right, if you were just say, for example, doing f plus g, right, that's adding the y values together at each x value, right? And then you're taking the derivative of that summed function f of x plus g of x. You can separate that out and take the slope instead of taking the slope of the resulting graph, you can take the slope of each graph and add them together and you'll get the same thing. So accordingly, we have f prime of 4 is 5. So this is 5 plus 3 times -5. So the g prime of 4 is the same as it was before. So 5 plus -15 is -10. Okay. Just for funsies, I'm not going to box the answers. I don't know why, but I just don't particularly want to. I don't know why. Okay. Same deal for this difference. The difference law is effectively the same as the sum law, where you can just split it up. So addition, subtraction typically follow the same logic, if you will. So g minus f prime of 0 is equal to g prime of 0 minus f prime of 0. Great. So now we're going to have different ones, though. So g prime of 0 is -6. F prime of 0 is -3. -6 minus -3. So -6 plus 3, which is -3. D. F of g prime of 1. So another way of writing this is f of g of 1. Or yeah, f prime of g of 1. That's another way of writing this. And I actually like this way better. It's clearer to me. So ultimately, this is equal to the result of all of it, regardless of how you write it, is it's f prime, or let me write it differently. F of g of 1. I'm going to do that and then take the derivative of the whole thing. That's equal to f prime of g of 1 times g prime of 1. So this is actually the correct thing. This is because we're taking the derivative of this whole entity here. But again, this to me makes more sense. It may just has some more parentheses, but what we're looking at is that it's this function f of g of x, right? Which is equivalent to this other f of g of x. Same thing, right? Same exact thing. Uh, it just, to me, makes it clear what the input is. So g of x, the whole function g of x is being input to f of x. That's what we're doing here. And what this right-hand side is saying is that we take the derivative of the outer function, f being the outer function. We take the derivative of the outer function with respect to the inner function, and then we multiply that times the derivative of the inner function, since the inner function, g of x, is itself a function of x. We still have to take the derivative of the inner function, and the relationship between that is a multiplicative one. That's what this is saying. So this later on, maybe you'll have already talked about this, but I'm pretty sure it gets discussed a little bit later. This is called the chain rule. And I have an analogy that I use for the chain rule called the Russian doll method. And we'll look at that perhaps a little bit down the line. But perhaps, yeah, when we actually get to particular functions that need to be derived using the chain rule. So look forward to that. But here we go. Let's answer this. So f prime of g of 1. So first things first, let's look at g of 1. So just g of 1 is 0. So this is equal to f prime of 0, right? So g of 1 just simplifies to 0 times g prime of 1. So g prime of 1, that is 1. So f prime of 0 times 1 is just going to be f prime of 0, right? Times 1 will just be itself. So f prime of 0 is -3. So -3 times 1. So just -3. All right, onwards. Now it's g of f, in parentheses, prime of 2. So g of f prime of 2 is equivalent to g prime of f of 2 times f prime of 2. So f of 2 is going to be 1. So g prime of 1 times f prime of 2. F prime of 2 is 3. And then g prime of 1 is 1. So 1 times 3 is 3. There's your answer. F. G over f, in parentheses, prime of 3. So now we get introduced to what's called the quotient rule. So we have g over f prime of 3. Right? So we had the sum law, and we had the difference law, but now we get into, well, there's also something called the product rule, or whatever, product law. I don't know if they also call it that, but the product rule. And then we also have this quotient rule. So whenever you have a ratio of two functions, g of x, and I'm going to rewrite it as, let's call it f of x over g of x, right? And we take that in parentheses or brackets, and we're taking the derivative of the quotient, right? So a fraction, another way of describing that is the quotient. This is the way that I go through that process. So the first step is to square the bottom. So g of x squared. And then step 2 is I'm going to plop that same g of x. So step 2, g of x on top times the derivative of the original top, so f of x, minus, let's call this 3, call this -4, and it's going to differentiate ourselves from the product rule, which we'll see just here in a second. I'll bring that up, even though we're not addressing a problem that directly uses it. Okay, step 5 is then g prime of x, and then step 6 is f of x. So you can see on either side of this minus sign, we have one function being constant as it was originally, and then the other function, we take the derivative of it. And of course, on the bottom, we have this g of x squared. So I'm going to quickly go through the same thing, but for a product. Okay. So we're going to see how similar it is to the quotient rule. So I'm going to do it in a very particular way. So I'm going to keep g of x times f prime of x plus this time g prime of x times f of x. So you can see it's super similar in terms of you keep one constant, you take the derivative of the other, and then you flip them, right? The one that was constant, you take the derivative of, and the one that you took the derivative of is now constant. And just really quickly, I'm going to show you how the quotient rule is the product rule, but with a slight twist. And it involves our chain rule. So I'm going to rewrite this f of x over g of x. So f of x times g of x to the negative 1, right? So anything to the negative 1, x to the negative 1 is equal to 1 over x. We can explain why that is another time, but for right now, just bear with me. So this is equal to the f of x over g of x is equal to f of x times g of x to the negative 1. And again, we're taking the derivative of the whole thing. So actually, I don't even know if, no, it doesn't. Well, okay, I'll be quiet. So we're going to apply our product rule in this situation. So we're going to keep the second one as is. So g of x to the negative 1, okay, times f prime of x plus, now we're taking the derivative of this entity here. So now it's not just g of x, but it's g of x to the negative 1. So we have a power rule situation. So we're going to bring down this exponent as a coefficient, negative 1 times g of x, right? Subtract 1 from the exponent, so now it's negative 2, negative 1 minus 1, so negative 2. And the chain rule aspect comes in, since it's not just g of x by itself, it's g of x raised to another power. So that's kind of, there's two functions going on there. And I will actually explain my Russian doll method. So what this is saying is, what the Russian doll method is you look to the outside first. So if you put a finger over what was inside here, right? So just like a Russian doll, you don't know how many layers deep the Russian doll goes. So you just are looking at the outer layer, which is something to the negative 1. So granted, when we're actually solving these problems, we can see what is inside, but we're taking it just as if the inside is just a black box for now. So it's this something to the negative 1 becomes negative 1 times something to the negative 2. Now that after we take the derivative of that outer layer, we peel back a layer, we take that outer doll, put it to the side, right? Now it's off to the side, that whole first layer. Now we can look that one layer deeper, and it's just this g of x. So we take the derivative and we have g prime of x. So the Russian doll method becomes extremely useful, or just the Russian doll concept becomes extremely useful when you have these multiple layers, because it enables you to, instead of having to write out what all of these different functions are, you just go layer by layer and you remain focused and just looking at what each of the terms is, and you go as deep as you need to without needing to artificially try and keep track of everything. But in this case, it's just two layers. We have the negative 1, the something raised to the power of negative 1, and then that something is g of x, where the derivative is just g prime of x in this case. Okay, all that, great. Moving on. And then times f of x, just like our previous product rule. So now let's look at this. So we have, on the left-hand side of the plus sign, we have g of x to the negative 1 times f prime of x. And on the right-hand side of the plus sign, we have negative 1 times g of x to the negative 2 plus g prime of, or times g prime of x times f of x. So again, all of this matches up except for if we were to try and get it. Okay, first let me rewrite this. So what this is f prime of x divided by g of x. We have plus, but then we have this -1, so it's minus g prime of x times f of x all over g of x squared. So now to get it to look like our quotient rule, all we have to do is make it a common denominator, which means we multiply the left-hand side times g of x over g of x. And then we get g of x times f prime of x minus g prime of x times f of x all over g of x squared. And that is my explanation of how the product rule and quotient rule are actually identical if you were to simply rewrite g of x as, or the divided by g of x as times g of x to the -1. Again, I hope that's really helpful. Once that clicked for me, it was just like, oh, if I theoretically forgot the product rule, I could just do, excuse me, forgot the quotient rule. I could just do the product rule and still get the same answer uh, to jog my memory. And it goes to show the larger point in mathematics is that if you really understand the concept, you actually don't have to really memorize anything because you can always rederive the situation. Okay. So we have g over f prime of 3. Is that correct? G, yeah, okay. So the quotient rule would tell us that this is equal to, so now it's flipped, right? So it's not g on the bottom anymore, it's f on the bottom. So we have f, not prime, but f of 3 squared. And then on top we have f of 3 times g prime of 3 minus f prime of 3 times g of 3, right? So it's just flipping the order of f and g in this case. Okay, so f of 3 is -3. G prime of 3 is 0 minus, well, on the bottom we can put this -3 squared. F prime of 3 and G of 3. F prime of 3 is -2 and G of 3 is 1. Just double check. Okay. So -3 times 0 is 0 minus -2 times 1. So minus -2 over -3 squared is +9. So we have 0 plus 2 over 9. So it's 2 over 9. Boom. So that's F. Awesome. Number 4, find the slope of the tangent line. They just want the slope, okay, to 2g of x at the point 1 comma 10. So really what we're looking for is g prime of 1. That is equal to the slope of the tangent line. That's it. They don't want the equation of the tangent line. Just stop there. So g prime of x we need to find first. So we're taking the derivative of this function. So we're going to use, again, we're going to use the quotient rule and the product rule. So this is going to be a fun one. It's enough work just to do the derivative. That's why they're, I mean, maybe that's why, but that's why they're not having you do the full thing. So first of all, on the bottom, we just square the bottom, x minus 2 squared, plop that x minus 2 top left, and then we're going to take the derivative of the top, which again is that now it's a product of two different functions. So we're going to keep the second one constant first. So that's our g of x times f prime of x. So the derivative of x cubed minus 2. So x cubed, the derivative is 3x squared. Derivative of a constant is 0. And then again, this is all the product rule. So we have a plus in between. Now we switch which one we're taking the derivative of. So the derivative of 3x plus 7 is 3 plus the derivative constant is 0 times x cubed minus 2. Boom. So that's the derivative of the top, that whole bracketed part there. Minus, right now we're back to our quotient rule. Now we take the derivative of x minus 2 is just 1 minus the derivative constant is 0. Right? And the derivative of x being 1, just as a refresher, it's basically y equals 1x plus 0. That is equal to y equals x. And the slope of that is 1. Just solid little note there. Okay, 1 times, now we just copy paste the original top. So x cubed minus 2 times 3x plus 7. So that's our g prime of x times f of x being the top. Great. And now we do, like, it would be a whole nother step to try and simplify and or expand this. We're not even going to go there. We're just going to now do g prime of 1. Just going to straight plug and chug, as they say. So 1 minus 2, 3 times 1 plus 7 times 3 times 1 squared. So you can see I like to put parentheses whenever I'm plugging in a value for x or y for that matter. Just to, when I go back and check, then I have clear evidence of what I'm plugging in where. Especially when the numbers are not so straightforward as 1, or like you can have like if we were doing x equals 3, there'd be a lot of 3's everywhere. So it's just nice to differentiate. 1 cubed minus 2 minus 1. This 1 times can kind of drop out. So 1 cubed minus 2, 3 times 1 plus 7, all over 1 minus 2 squared. Okay, so 1 minus 2 is negative 1 times 3 times 1 is 3 plus 7 is 10. 1 squared is 1 times 3 is 3 plus 3 times 1 cubed is 1. 1 minus 2 is negative 1. So yeah, 3 times negative 1 minus 1 cubed is 1 minus 2 is negative 1 times 3 times 1 is 3 plus 1 plus 7 is 10. Again, all over. Now it's negative 1 squared, which is just 1 on the bottom. So 10 times 3 is 30 plus 3 times negative 1. So that's minus 3. 30 minus 3 is 27. 27 times negative 1 is negative 27 minus negative 1 times 10. So it's negative 10. So let's call it plus 10. Or we can do minus negative 10 just for funsies. All over 1. So that's just 1. So negative 27 minus negative 10. So plus 10. So that's negative 17. That's RM. Boom.